Calculus is one of the most important fields in mathematics, widely used in physics, engineering, economics, and many other disciplines. At its core, calculus is a way of understanding change and accumulation. When we talk about change, we're often interested in how fast something is moving or growing. For example, how fast is a car traveling at a given moment? Or how quickly is the value of a stock changing? These questions are all about rates of change. Accumulation deals with adding up small quantities over time, such as finding the total distance a car travels or the total amount of water that flows into a reservoir. Now, let's dive into one of the most fascinating ideas that calculus deals with: infinity. Infinity is a concept that's often hard to grasp, but it plays a crucial role in calculus. Think of infinity as something that never ends. When we talk about an infinite number of points on a line, or an infinite number of moments in time, we're thinking about something that goes on forever. Calculus helps us work with these infinite quantities in a precise way. For example, we can ask questions like, what happens to a function as its input gets larger and larger, approaching infinity? This is the beginning of an idea called a limit, which is fundamental to calculus. A limit is the value that a function or sequence approaches as the input gets closer to a certain point. Imagine walking toward a wall, going halfway with each step. You'll never actually reach the wall, but you'll get closer. This is similar to limits in calculus, where the function approaches a value without reaching it. Limits are the foundation of calculus, helping us understand quantities that are infinitely small or large. Consider the function 1x as x approaches 0. As x approaches 0, the value of the function grows larger, approaching infinity. This illustrates how limits reveal the behavior of functions. The next concept is derivatives, describing rates of change. Imagine tracking the speed of a car. The speed at any moment is the derivative of distance over time. Calculus allows us to calculate speed with precision, even at extremely small time intervals. A derivative is all about measuring how a quantity changes over time. For example, if you're driving a car, you might want to know your speed at any given moment. That speed is a rate of change. It tells you how fast your position is changing over time. The derivative helps us calculate this rate of change exactly. Imagine drawing a graph of your car's position over time. The slope of the line at any given point tells you how fast you're going at that moment. If the slope is steep, you're going fast. If it's flat, you're not moving at all. To compute a derivative, we look at how the function changes as we zoom in closer to a specific point. This ties back to the concept of limits. We're interested in what happens to the function's value as the input gets closer to a certain number. The derivative is the limit of the slope of the secant lines. In essence, the derivative is the slope of the tangent line to the curve at a specific point. This process can be used to study a wide range of real-world phenomena. In physics, derivatives help us understand motion. In economics, they help us understand how costs or profits change as we produce more. In biology, derivatives help us track how populations grow over time. The applications of derivatives are virtually endless. While derivatives deal with change, integrals deal with accumulation. Think of integrals as adding up a lot of small quantities to find a total. For example, if you want to know how much water has flowed into a reservoir over a certain period of time, you would use an integral. The integral helps you sum up all the tiny amounts of water that flow in during each moment of time, giving you the total amount at the end. In mathematical terms, integrals are often described as the area under a curve. Imagine drawing a graph of the rate at which water flows into the reservoir over time. The area between the curve and the x-axis represents the total amount of water that has flowed in. Integrals allow us to calculate this area precisely. The process of integration is essentially the reverse of differentiation. While differentiation asks how fast is something changing, integration asks how much has accumulated. Just like derivatives, integrals have countless real-world applications. They're used in physics to calculate work, energy, and electric charge. In economics, they help us calculate total profits or costs. In engineering, integrals help us design structures that can withstand varying forces over time. The beauty of calculus lies in the deep connection between derivatives and integrals, expressed in the fundamental theorem of calculus. This theorem states that differentiation and integration are essentially inverse processes. If you take the derivative of a function and then integrate the result, you end up back where you started, and vice versa. This connection makes calculus incredibly powerful. We can use derivatives for rates of change and integrals for accumulation. In the real world, this means we can understand how systems evolve over time, predicting changes and accumulations. Whether studying the motion of planets, the growth of populations, or the flow of electricity, calculus provides precise tools. These concepts may seem abstract, but they profoundly impact how we understand the world. From understanding changes at a moment to calculating total impact over time, calculus offers a powerful lens. If you found this explanation helpful, like, share, and subscribe for more fascinating topics. Keep exploring and learning.